Hey grade 8s, welcome to your Friday math lesson. So right off the bat, I say this a lot, but I want to keep on saying it because it's absolutely true. You guys are doing an absolutely amazing job. I'm so incredibly proud of all of you. This is not an easy challenge to rise up to. Like you guys, some of you I know of you are humble and thinking like, oh, this is nothing. Like, no, this is a hard challenge to rise up to in many ways, more than one, not just education wise, but with everything going on right now. Like I am deeply impressed by all of you, and I know it's tough. It's tough for all of us. I do hope you guys are, of course, taking the steps necessary to take care of yourselves as well. It's stressful, I'm hoping, especially now that we're getting closer to the end of the year and going into summer, that things will continue to improve and things will open back up and everything. But no, you guys are doing an absolutely amazing job. Hopefully you've been able to enjoy some of the weather and all the sunshine we got. I went out for a couple hours the other day and I already got sunburnt, so it's the mark of the end of spring, beginning of summer. All right, so today is our last day of doing our coordinate plane. We are doing a little bit of a different activity or different kind of worksheet or our homework or assignment to go with this lesson. It's just because of the reality of this type of use of the coordinate plane. It doesn't use a regular worksheet. Now, you'll understand when I get to that second part. For now, let's just do the review. So we have our shape here. It has the coordinates already given to us, and we need to rotate it 90 degrees clockwise. So if it's rotating clockwise, we know it's going to go this way. If it's only 90 degrees, we know it's just going to end up in this quadrant right over here. So it's going to end up in quadrant 4. So we know it has to end up here. When we're in quadrant 4, we know our first digit is going to end up being a positive one, and our second one will be negative. Now we just have to figure out how we have to change these digits or change the coordinates. So if we have 2, 2, well, we know for 90 degrees and 270s, we have to switch them around. There's no point in switching 2, 2 around because it just makes 2, 2. We just have to figure out which digit is going to change into a negative number. And we know that the first digit must be positive because if the first digit was negative, we'd end up over here. So it has to be positive because our first digit, if our first digit is positive, we're going to end up on this axis right here. And if our next one is negative, we're going to end up over here and we're in the right quadrant. So we know that it has to end up being 2, and our second digit needs to be negative 2. So we have 2, negative 2, and that's 1 point. 4, 4, we don't need to switch them around, and we know our second one is going to be negative right off the bat, because if the first one is negative, then, if the first coordinate, we know that the second one is negative, they're all going to follow that same rule. So it's going to be 4, negative 4. And now our last one is 4, 2. We know we have to switch them around for a 90 degree, so it ends up being 2, 4. And we know now our second digit is going to be negative. So we go 2 down to negative 4. And here is our rotated shape. And there we are. Our lesson for today. So as I said, we're going into real-world applications of the coordinate plane. Right off the bat, you might think, well, when is this ever going to be useful in real life? Believe it or not, the coordinate plane actually plays a big role in day-to-day life. And in many ways, we don't see what it is. But one example I can tell you is maps. They're used all the time in maps because what's nice about a grid like this that has an X and Y coordinate, you have a center, you have an origin point. So let's say if you were plotting out a city, you can have your town hall in the center because the town hall is usually around the center of a city, and then it ends up being kind of a grid pattern. Lots of cities end up following a grid pattern all the way out. You'll see older cities don't necessarily follow this, but modern cities like Canadian cities do. They follow this kind of a grid pattern. Why is this significant? Well, when you're planning a city, for one, if you have an origin, it's really nice because you can just plot out your town hall in the middle. Because if you have a regular grid like this, and your town hall's in the middle, it doesn't work as well because here you have points like a compass. You have north, east, south, and west. So you can really plan out a city this way. So believe it or not, when cities were originally planned, a grid system like this would actually be used. Because, as you notice, like cities follow a grid pattern. Streets follow grid patterns because they go north and south, east and west. So this is how coordinate planes can be used in real world. It can be used for planning a city. Another way they can be used is if you ever look at a globe, you know that there is an equator that runs around the globe, that runs east to west, or west to east, whatever you prefer. It goes all the way around the globe. As some of you may know or may not know, there's a second equator that runs north to south. So this one runs vertically around the world. This is significant because if you're ever looking at world maps, it allows you to graph out where points would be on a map. If some of you guys remember when we had Indigenous Day back in February, we had that huge map on the floor of the gym that you could walk on and everything. On that map, I don't know if any of you noticed, but there was actually grid patterns. They weren't perfect straight line grids. They were kind of like this because it was trying to show you the curvature of the world. But they were grids that ran like this. And that runs around the world. And those are used, and it had latitudes and longitudes. So you learn a lot more about them in grade 9 geography, by the way. But that's another way that the coordinate plane is used because latitude and longitude is based off of a coordinate grid. Because once you go past the equator, you start getting into negative latitudes and longitudes, and then you go things like that. So that's why those two equators are significant, because when you go into separate sections, that's where you mark positive and negative latitudes and longitudes. So what we're doing today, I'm going to show you an example. And this is going to be a little bit of a revisit back to Pythagorean theorem. If you guys remember that, we're going to go over it again. So if you don't remember it very well, don't worry about it. But we're going to be talking about a real world application where you would use this grid. So let's say, for example, my house, I live in a town and my house is right here. So I'm just going to mark H for house. It's at -4, -3. The town hall is in the center of the town, and let's say I want to go to a restaurant, which is over here. So I'm just going to put R for restaurant, and the restaurant is at 1-4. So if I'm driving, I can use translations to figure out how to get me, this point here, where I'm at my house, all the way to the restaurant. I go so many units up, and I go so many units to the right. Or I can go so many units to the right and so many units up to get from one place from my house to the restaurant. What if I was walking though? I don't want to take this long route from here to here. That would suck to walk. I'd prefer to take a shorter way. So I could go this way. However, I can figure out these distances here very easily, but I can't figure out this distance by just looking at a grid. I can't count the square units. This is where our Pythagorean theorem comes into play. So we have A, B, and remember our longest angle, so this angle right here is always C. Remember, C is always, always, always the longest one. A and B can be interchanged. It doesn't really matter as much, but C is always the longest side of a right triangle. It has to be a right triangle. What's our formula for Pythagorean theorem? A squared plus B squared is equal to C squared. So I want to figure out this distance from my house to the restaurant. So if I was walking, I could tell you, oh, it's this many units north, or let's say each unit represented a kilometer. So each marker represented a kilometer. I could say it's this many kilometers north and this many kilometers to the right if I was driving. Because if I'm driving, I can't cut through diagonally usually. I usually have to follow the roads, unless I'm driving through people's lawns, which I don't think would work out very well. But you can go north and east to follow those roads. So I can go like, oh, I go north on this street and right on this street. However, if I'm walking, I can take a shortcut. This is, of course, assuming that I can just take a direct route there and there's nothing blocking my way. So we need to figure out what this distance is. So we have a squared, which is a is 1, 2, 3, 4, 5 units. So it's 5 squared plus b is 1, 2, 3, 4, 5, 6, 7 units. So we have 7 squared is equal to c squared. So remember, we deal with square roots, so we have to basically do 5 times 5, which is 25, plus 7 times 7, which is 49, is equal to c squared. As some of you guys have found out, maybe when we were doing Pythagorean theorem the last time, if you have an iPhone and use the calculator on that, there's not really a square root button like a normal one. It's a different type of one. Just reminding you guys about that because I was trying to use my phone earlier and then I completely forgot about that. I'm not sure about Android, but anyway, I'm getting off topic. So we have 25 plus 49, which gives me 74. So 74 is equal to c squared. What's my last step? I need to find the square root of this. So I have to find the square root of 74, which is 8.6. So that, therefore, c is equal to 8.6. So remember how I was saying like each square unit is a kilometer? I could then say the shortest path or the shortest route from my house to the restaurant is 8.6 kilometers. And I can say, oh, from my house to the restaurant, I'm going in a northeast direction. So from my house to the restaurant, so if I was writing directions, let's say, I'd say I go northeast to the restaurant for 8.6 kilometers. So what you guys are going to be doing today is you're actually going to write 2 real-world scenarios. My recommendation is try doing a smaller one, like maybe from your house to the school or something like that. Make sure you're only going north or south and like you're only going so many units up or over, because if you start going in different directions like this, then this, and then this, and then this, like that obviously won't work. It has to be basically like 1 and 2 or 1 and 2, 1 and 2, something like that. It has to be that L shape, and then you're trying to find out the hypotenuse or the long angle to figure out the distance. You will have a Google form available to you if that's what you prefer to use. However, if you prefer to actually draw it out to describe it, do that and send me a picture. If you don't really like uploading things to the VLE, don't worry, send me an email and I keep them all in a separate folder in my email anyway, so I have them, so I make sure I don't lose anything. So it's there. What you're going to be doing is you're going to write 2 real world scenarios. You can do one that is like from your house to somewhere else, and then I recommend also trying to do a bigger scale one. If you want, you can do 2 small scales, I don't mind. They just need to be unique. It can't be like, oh, your house to the school and then from the school to somewhere else. Like, try to make them a little bit more unique than that. And you're going to actually the big thing I want to see is the math. I'm not so worried about the language. You can describe to me like I need to know like what direction it is and the original points. So make sure like you give me points on a coordinate grid for like I gave you the points for my house, which was -4, -3, and then the restaurant was 1, 4. Like, make sure you're giving me points, because then you can tell me, like, oh, the shortest route from -4 to -3 to 1, 4 is blank square units. In this case, it was like 8.6 square units. I want to show you guys one way about using on a large scale. So let's say we're using this as a world map. And let's say Canada is about here, and let's say Australia is about here. So this is C for Canada and A for Australia. When a plane flies, it obviously doesn't go this many units right and then this many units down. It finds the most direct route if possible. So it flies across. Or another way is it crosses, and then we can also say, like, oh, look, it crosses this equator, it crosses this equator at a certain point. That's not really relevant. I'm just saying that because, believe it or not, you're going to actually be doing a lot of this in grade 9. So, little hint, hint. But we're trying to find the shortest unit from Canada to Australia. How do we find that? Well, I can't just count square units. Even if I had perfect diagonal units like you see here, I can't count those, because remember, the diagonal angles, obviously, that line is a lot longer than this line. So I can't do that. So how do I do it? Well, I use my Pythagorean theorem. So if this was a world map, this is obviously not completely accurate, but for the sake of this, this is our example. Our coordinates for Canada are -3, latitude, and longitude goes up and down. So let's say our points are -3 and 4. So let's say, for example, Canada's latitude and longitude was -3, 4. Australia's is 5, -4. I need to figure out the distance from Canada to Australia, so I use my Pythagorean theorem. A will be here, B will be here, C is always, always, always our longest angle, or longest side. So I need to figure out what C is. To do so, I basically go 1, 2, 3, 4, 5, 6, 7, 8. So 8, or A is equal to 8 units. Let's say, for the sake of this example, 1 unit is equal to 1,000 kilometers. It's not actually, it's much bigger, but I'm just using this for an example. And B is 1, 2, 3, 4, 5, 6, 7, 8. So B is equal to 8,000 kilometers as well. I need to figure out what the distance of C is. To do so, I use my Pythagorean theorem. So I do A squared plus B squared is equal to C squared. So A is 8 plus 8 squared is equal to C squared. 8 times 8 is 64 plus 64 is equal to 128. Now I have to do the square root of this, so square root 128. So, sorry, I'm just punching this in quickly. Is equal to 11.3. So therefore, 11.3, therefore, 11.3 times 1,000, because it's 1,000 kilometers. The distance from Canada to Australia is 11,313.7 kilometers. So what you're going to end up doing today is you're going to write 2 scenarios. You need to make sure you give me coordinates. So give me a coordinate of your original point to where you're going or something like that. And if you want to plot it out on a grid to show me, because it helps you think it through better and also helps you, do so. Send me a picture. You can send it to me over email. If that's what works for you, do it. If not, if you're happy to basically just write it out under Google Docs, you write 2 separate paragraphs, one for like a small scale, one for a big scale, for example, then you can do that. Absolutely. Just make sure you describe to me the math. So, for example, my house is at point -34. The park is at 5 -4. To get from this to this, it would be so many units right and then so many units down. But the shortest route is 11.3 units across. Therefore, like this. I can totally accept something like this. I'm not expecting a really long paragraph. The thing I just want to see is the math and also like your application to where you can use this in the real world. If you guys want to get creative, look at some other ways it's used in the real world. The most common is mapping. That's right off the bat what it's mainly used for. Military uses it a lot. City planners use it all the time. Things like that. You'd actually be really impressed about how much it's used. Like I used to work at a bank and we used it to show where different points were. Like I used to work at a bank over summer when I was in university, and we would show it to show where the different branches are in a city, and like the origin would be like the city center or downtown. Like that's another way that it would be used. You'd actually be surprised. If you guys want to look up some other ways that it's used and some other ways that you can show like movement on a coordinate plane and how it's used, go for it. This is definitely meant to be a more unique homework, but it should be pretty easy and I think a nice way to end out this unit. So I hope you guys are doing fantastic. Enjoy the nice weather we're supposed to be having, and I will see you guys on Monday. Be sure to email me if you have any questions whatsoever. All right, see you guys.